Okay, now we start from this slide. What we have done in the last class was we discussed about the closed frequent item set mining and the maximum frequent item set mining. Now, we told you that maximal is the subset of closed and closed is the subset of frequent item set mining. Now, today we discuss one more algorithm, which is a very, very good algorithm called as the frequent pattern tree algorithm. But before that, let me just discuss what are the factors which affects the complexity of the algorithm. Now, obviously, I told you in the previous class that how you are going to take the minimum support will decide the complexity of the algorithm. Why? Because it's not possible to change the minimum support every now and then and run the algorithm again and again. Because if you keep on doing like this, every time it will take a lot of time to generate frequent items, and you will have to do it in such a way that you have to use it at a multiple level of support. Now, since you are doing programming in Python and already there are functions for that, therefore that's another part of the whole algorithm. But as far as the algorithm is concerned, it does not contain any method where you can try to find it in a faster way. Therefore, when you are going to use a lower support threshold, therefore obviously you will get more frequent items, and if you are going to use a higher threshold value, you will get lower number of frequent items. Okay, and similarly you will get the length of the transaction the length of the candidates will also increase as and when you are going to take a lower threshold. Therefore, you have to take a support such that it should be interesting for the end user or for the decision makers. Now, the second one is called the dimensionality, and dimensionality is the one which tells you that how many number of items are in the data set. Now, if the dimension is very large, you require more space to store them and to count the support. If the number of frequent item increases, it will also increase the computation time as well the input-output cost. Why? Why I say input-output cost? Anybody can give an idea why I am going to say input-output cost? Why, if the dimensionality increases, the IO cost also increase? Can anybody answer this question? Anyone? Why the IO cost increases? Because you have to bring the particular transaction from the hard disk to the RAM. Because initially the database will reside in the hard disk or the secondary memory, and once you are trying to run the algorithm, that data must be loaded in the primary memory. Therefore, the time will increase when you are going to do a lot of swap between the main and the secondary memory. Now, third factor is the database. Now, since the a priori makes multiple pass, the runtime of the algorithm will increase with the number of transactions. I already told you, because in order to find two item set, you have to scan the database. To do it for in k is equal to 3, you have to again run one scan. K is equal to 4, you again have to run one scan. That means when you are generating L1, you require one scan. When you are generating L2, again one scan, and keep on going until you are going to generate L of k. Therefore, when I am going to generate this L of k, I am going to do at least k scans. Of course, I will require k scans. And the fourth factor which comes is the average transaction width. We say that when the transaction width increases, it will always, when the data set is dense, the transaction width will increase. Now, this will increase the maximum length of the frequent item sets, and therefore, when you are maintaining a traverse hash tree, it requires more traversals because the width of the tree will become more. And these are the four factors which affect the complexity of any algorithm which is going to use the frequent pattern mining algorithm. Okay. Now, Based on this, let us try to get some other algorithms which is much better than a priori. Obviously, there are some limitations of those algorithms, but if you're going to see from the speed point of view, those algorithms are much faster than a priori. Now, how do you generate the rules? Now, till now, what we have done, we know the frequent items. For example, I can say A, B, C is frequent. But how to generate the rules from this? Now, let us try to get this concept. You are given a frequent items, which are basically which contains, say, it is having an L, which is the list of frequent items, and these are the items which are L, which are frequent. Now, our aim is to find all non-empty subsets F, which belongs to us. Therefore, we want to find F, which is subset of L, such that F is equal to L minus L. Now, it means that you want to generate F from those L such that F is equal to L minus L, and that satisfies the minimum confidence requirement. That means, suppose if I say ABCD is frequent, now from this you generate lot many rules. What are the rules I can generate? I can generate, say, A follows B, C, D. I may say B follows C, D. Then I say C follows A, B. And therefore, you can generate 2 to the power of 4 number of rules. Therefore, since there are four item sets, therefore I generate, in this case, I will generate 2 to the power of k number of rules. 2 to the power k number of rules, which is equal to 16 rules. But what happens when you are going to generate 16 rules? 2 rules what you are going to generate are not that important. Why? Because those do not give you any particular information about the frequent items. And what are those rules? Those are, this is the rule which says 5, and this is the power set. That means those 2 rules which say that when L follows 5 and 5 follows L, that means you are having 2 rules which is nothing but a null set and a power set. And therefore, if you are going to get this, actually you are going to decrease 2 from this. And I will be getting over here as 14 rules. And you find the other 14 rules over here. The other 14 rules. Therefore, from this 4 item sets, I can generate 14 different rules. I can generate 14 different rules. And this is how you are going to generate rules from the list of frequent items. Now, try to find the complexity involved. I have only one frequent item containing 4 items, and you generate 14 rules from this. And therefore, the length of the item set is only 4, and you get only one frequent item set. And therefore, you will get lot of rules which are not interesting. And therefore, the problem with these frequent pattern algorithms are they generate lot of rules which are not interesting. And how will I going to cut down or prune those rules? There is a whole lot of concept to be followed. That how I am going to generate only those interesting rules over there. Now, this is a general technique to generate all rules. To generate all rules. Okay. Now, how you are going to generate the rules? Now, it is what I do. If I am getting a particular item sets are there, what you have to do is that you have to generate the rules with the support and the confidence. But you know that confidence do not have the anti-monotone property, whereas the support has an anti-monotone property. And you remember the anti-monotone property is that the subset of an item set, the superset of any frequent item set will not have the support greater than its subset. Whereas in confidence do not have this anti-monotone property. It means that the confidence of this rule can be larger or smaller than this rule. And you see this one is a subset of this one. Therefore, I cannot say whether the confidence of ABC follows D is more or AB follows D is more. For support, this will not be there. But you have to know this also, but confidence of rule generated from the same item set has an anti-monotone property. That means if you are going to generate the confidence, generate rules with a confidence from one item set, those which you are going to generate will always have an anti-monotone property. Now the meaning is this: if I am having this ABCD and I am generating the rules like this, one rule, second rule, and third rule. Now here I can say with surety that the confidence of this rule, the first rule, will be bigger than or equal to second rule, or will be bigger than or equal to third rule. And you say this is a subset of this, and this is a subset of this. This is a subset of this, and this is a subset of this. Why? Because ABC, AB, and A are generated from ABCD. And therefore, we can say that these support the rules which are generated from the same item set has an anti-monotone property. Okay. Therefore, what is the statement I can say? Confidence is anti-monotone with respect to the number of items on the RHS of the rule. That means if on the left hand side, if it is having more number of items, it will have a higher confidence. And you see in the first one you have 3 items, in the second you have 2 items, in the third you have only 1 item. And therefore, confidence is anti-monotone with respect to number of items on the RHS of the rule. This is the property which will hold. Whereas, if you find from in general, confidence do not have an anti-monotone property. Correct? Now let us try to. Now this is one of the things which you have to just show you. For example, I am having some lattice like this, and where you find that these rules, for example, BCD, over here I have some low confidence rules. And if I am having a low confidence rules, just when I say that you are going to generate all those rules which are generated from BCD, will having a lower confidence. Now you find over here, this is also a subset of this. This is also a subset of this above rule. This is also a subset of all the above rule. And all these are subsets of the rules on the left hand side. And therefore, you can easily prove these rules. Why? Because if BCD follows A is having a low confidence, the subset of this will always have a low confidence, or a lower or equal lower confidence, because this property, I just discussed this property over here, that this property over here will tell you about this one. And using this property, I can very well prove these rules, because I find that this rule itself is having a low confidence. And therefore, I don't need to test for all. I will just prune those rules from there. And therefore, you are getting a smaller number of rules using the a priori algorithm. Okay, you are getting a small number of rules because you are applying a pruning technique to prune the rules. And using the anti-monotone property, we say that rules generated from the same item set will be having a lower or equal confidence. Therefore, by that, if I know that BCD follows A is having a lower confidence, all rules generated from that will have a lower confidence. Okay, fine enough? Good. Now this is the how you are going to now just in summing up. candidate rules is generated by merging two rules that share the same prefix in the rule cluster. Now, if I am having these two rules, okay, and I have from these two rules, I can generate one rule because you find that D is common over here. And what I can do, I can take the A, or I can generate over here D is equal to ABC. Now AB will come here and AC will come here. If I can generate ABC and D follows ABC is generated from these two rules if it is having a common prefix. Okay. Now some rules will generate like this, and you can also prune the rules if the subset of this rule does not have a higher confidence. Now, if I generate these rules over here, now what I can do, I can check the confidence. If the subset of this rule does not have a high confidence, I can prune the rules. Now, what are subset of this? You just check over here with this one. The subset could be, one of the subset will be like this. Another subset will be like this. Because these rules are generated from ABCD, and therefore this doesn't, if it is not having a higher confidence, I can very well prune those rules from there. Now let us see the bottleneck of the trie algorithm. The core of a trie algorithm, that you are generating the frequent patterns of frequent item sets. From, therefore, what I get, I have a candidate K item set and I am going to generate K minus 1 frequent item set. You must be remembering that from C4 I got M4. Okay. Therefore, what we are going to do, the frequent, we are using the K1 minus 1 item set to generate candidates of K item set. That means when I say, I can say with L3 I generate C4. With L3, therefore I use with K minus 1, I generate K item sets. Okay. Now the problem what arises, that if you find that I have 10 to the power 4 frequent one item set, it will generate 10 to the power 7 candidates with 2 item sets. Now in order to discover the frequent pattern of size 100, for example, I want to generate a frequent pattern of size 100. For example, it may have A1, A2, A3 to A100. Now you have to generate around 10 to the power 30 candidates. That means if I want to generate only 2 item sets, I will generate 10 to the power 7 candidates. Now, if I want to generate a frequent items of 100 items, I generate 2 to the power of 100 or equal to, we can say, 10 to the power 30 candidates. And therefore, this number is so high that it's too difficult to accommodate in any particular RAM or even in a database. So this is one of the bottleneck of a query. And you know that you require multiple scans of the databases. Therefore, you require n-1 scans to generate the longest pattern. For example, I want to generate, say, L10. I have to do 11 scans. Why? Because 10 you want to generate for 10, and the first scan you want to generate the frequent one item set. Therefore, if you want to generate the longest pattern of length n, you require n+1 scans. Okay, fine. Okay, now let us try to see the second algorithm, which is a very, very good algorithm called the FP tree algorithm. And this algorithm is given by Kevin Han, the book which we are following. Now, how this algorithm works? For this algorithm, what we are going to do, we are going to compact a large database into a frequent pattern tree. Now, the crux of this whole algorithm is I have a very, very large data set. I have to convert that database into a FP tree. Now, FP tree is a frequent pattern tree, which is not a binary tree, but it is just like a tree with a hierarchical structure. It is very highly condensed, but complete. What is the meaning of complete? By complete, we mean to say that using that FP tree, I can generate the rules. That using only one FP tree, I can generate all frequent patterns. And therefore, the advantage is that you are going to avoid the costly scan of the databases. You are going to avoid the costly database scan. Because you know that in a priori, you require to scan n+1 times, but in this one, you do not require to scan n+1 times. Okay, and I will tell you in the latter part that how many scans you want, how many scans you require in order to generate a frequent pattern. Okay. Now this is based on a divide and conquer methodology. Now you know that a divide and conquer means you are going to decompose a bigger task into smaller ones, and you don't generate the candidates. You just read the tree from bottom to top, and you will be getting the frequent patterns. Now let us try to understand the algorithm. This has to be understood very well because it's a little tricky than the previous algorithm. Now suppose I am given this data set, which contains 5 transactions, and these are the items which you find that transaction number 100 contains FACDGIMP, and so on. I have this frequent patterns. Now, what you are going to do is that I have to take some minimum support. Now here I am taking a minimum support equal to 3. Now I will first of all scan the database to check the frequency of each and every item. Now what I will do, I will check the frequency of F. I find F occurs 2 times, 3 times and 4 times. Therefore I write F is equal to 4. Then I check for A, I get 1 time, 2 times, 3 times. Therefore I will write A is equal to 3. C, again 1 time, 2 times and 3 times and 4 times. Therefore I write C. Similarly for D, I will compare 1 time over here and nothing, no more. Therefore I just prune this because it is not frequent. Similarly take G, G only comes 1 time. Therefore I will be doing, I will just removing those ones over there. I will remove D. I will remove G. I again comes only 1 time. I will remove I. M, I will find that M comes 3 times. Therefore I will write over there. P, then this is okay. P, 1 time, then again 2 times and 3 times. Therefore this will also come 3 times. And just O and O, only 2 times. Therefore this will leave. Similarly, SI will not be there, and all these are not frequent. Therefore, all these will go off, and only you will find that there are only 6 items which are having a minimum support of at least 3. And what I do, I arrange it by the descending item frequency. Now that means I am going to put like this. That means the higher ones, F4 will come on the top, followed by 3 and so on. And of course you will have only 2, either 4 or 3. And if I get this, I am going to lexicographically sort this. Now here F is coming first, I will write F. Now here you just check what I am doing. I am going to use like this. I write F over here. Then C is coming over here, therefore I write C. Then A A is coming third, therefore I write A. M is coming before P, therefore M and P. That means this has to be ordered in the order what the table of item frequency is there. That means M will always come after B, P will always come after M, C will always come after F. Now you can ask, can I interchange C and F? Because these are having the same frequency. Of course, you can do that. You can interchange F and C, you can interchange A, B, and P, because all are having equal frequency. Therefore, I can write say C, F, B, A, M, P, or I can write C, F, M, P, A, B. But any one I follow, I will uniformly follow every time. Got it? Okay. Now I got this one as the new database. I got this one as the new data set. Now you just check the step, scan database once, find frequent one item set. Of course, when I maintain this one, I follow this one rule. Step 1, sorry. Then I am going to arrange it in descending order of support. This is the second one. That means the first two tasks I did here only. I completed these two. And the third task I will do now. What I will do? I will scan the database again to construct the FP tree. Now, here you will find the answer to the question, what I just discussed in the last slide. How many scans you require to construct FP tree? Any answers? How many scans you require to generate the frequent pattern tree? Anybody can give any answer to this? Yeah. Anyone? Please answer.
Sir, 2.
How many?
Sir, 2.
Okay, Abhishek 2. Anybody more giving any other answer? Correct. Abhishek is correct. You are therefore it requires 2 only, and therefore try to answer the questions, because whatever by the interaction which we are having, that will have your weightage in the overall evaluation. And I told you time and again that the evaluation will be based on the class interaction as well as the quiz which I am going to put from next class. Therefore, don't rely on the sessionals which is being taken, because this class has to be an interactive one. Therefore, I'm already having your sheet over here, and I keep on marking once you answer the questions. Okay, fine. Why 2? Abhishek, can you be precise? Why did you say 2?
So it was written on slide. First step was to arrange them for the support according to the support in decreasing order.
Correct.
Then in third scan, correct.
Yes, that's fine, because you know that. Therefore, this is too simple questions, because already you find that you are given over here. It's already written that you are having one scan over here and one scan over here. That means you require only 2 scans. How many scans you require in an a priori algorithm?
So n+1 for
n+1 scan. Therefore, in a nutshell, you must know that this particular algorithm is free from the K. Even if I am going to generate, say, an item set of, say, length 10, I require only 2 scans. Okay? It only requires 2 scans, irrespective of the size of the frequent pattern which I am going to generate. And therefore, this is one order of faster than the a priori algorithm. Fine. Now, let us try to see how you are going to do the algorithm. Now, this is the database which I have trimmed down, and you know that from this one, from this TID and this one, I just copy over here. and I am now generating the frequent pattern tree. Now with the frequent pattern tree, what I do is I am going to take the first one. I am going to take the first one over here, and with the first one, I check that this is FCAMP, and I am going to make a route, and for the path from here, like C FCAMP, I make a branch from the root with FCAMP. Correct? Now branch can be on left hand side, right hand side, middle, doesn't make any difference. Do not think that I am just putting it on left hand side. It could be because it's not a binary tree. Therefore, there is no left, there is no right, there is no middle. It could be any number of therefore branches. Now this one over here says that F comes one time, C comes one time, A comes one time, M comes one time, and P comes one time. Therefore, this one is the count. Now again take the second transaction, FCABM. Now from this one, you find that FCA is already there from the root. F is already there, C is already there. Therefore, if I check these three, you find that FCA is already there, and you can see F is here, C is here, and A is here. Therefore, I can use the same branch to generate FCA, but B and M is not there. Therefore, what I require is that from here I will make one another branch from here, where FCA will be common to the both transactions, and BM will be separate from A onwards. Therefore, I will write like this. And you find that I also updated the count of FCA. Why? Because now F has come 2 times, C has come 2 times, and A has come 2 times. Whereas B and M has come 1 time. And therefore, the count of B is 1 and the count of M is 1. Now you see one more thing. You might ask me that why the count of M is 2, but it is in 2 different branches. Now, what is the total count of M in the whole tree? What is the total count of M in the whole tree?
Sir, of 10 not 2.
32.
2. Why? Because 1 here and 1 here. And how many M you have encountered in the first 2 transactions? 2. Now, you just sum all the counts. 2, 4, 6, 7, 8, 9, 10. Right? F2, C2, 4, 6, 7, 8, 9, 10. And how many transactions, how many items you have find over here? 10. FCAMP, FCABM. And that means it is correct. The total number of count in the tree is equal to the number of items here in the database. Now let us take the third transaction, FB. And you find that F is already there. Therefore, what you require? You require to just take one branch from F and not from the root, because F is already there. Therefore, what I do, I take one more branch over here. And here I increment the count of F. If I increment the count of F from 2 to 3. Now I take the fourth transaction, CPB. Now what should I do? Yeah. What should I do now?
रूट से लेंगे सर.
Root से लेंगे. Why? Because
सर ऐप,
हाँ बोलो बोलो.
क्योंकि सर ऐप से शुरू है ना, तो ऐप के नीचे ही है.
Yes, because yes, correct, Javed. Because there is no C at the top. Therefore, you have to take from the root itself. Therefore, हमने बनाया, यहाँ से बनाया. I take like this, CPB. Correct?
Yes.
There is only difference. वहाँ पे CPB लिखा हुआ है. That's wrong. It should be CBP. Why CBP? Because B पहले आ रहा है P से. यहाँ जो लिखा है ना ये, इसलिए थोड़ा सा गलत है. I will just change it over here. Here, this should be CBP because B comes before P. But यहाँ सही है. It's correct over here. But here it's other way around. But doesn't make any difference. Even if you take reverse way, it will not make any difference. Now the last one, FCAMP. Now what should I do? FCAMP, you find that everything is there. Where? Is pathway. Therefore, in this case, I do not require to do anything except I just increment the counts. किसका करेंगे? F का, C का, A का, M का, P का, उस पाथ में जो आ रहा है, यानी इस पाथ में. And what I do? I increment the counts. Now, just to check whether the tree is correct, you just count the total number. Fourth is 7, 10, 12, 13, 12, 14, 15, 16, 17, 18, 19, 20. 20 are there. And if you count in the number, how many items were there? 20. पहले में 5, फिर 5 10, फिर 2 12, फिर 3 15, 5 20. इसके मतलब कि जो ट्री है वो सही बना है. We have not missed any items. कितना स्कैन लगा? एक स्कैन. बिकॉज हमने एक ट्रांजेक्शन को पढ़ा और एक ब्रांच बनाते गए. Now this completes the FP tree. Construction is over. Now what remains? How to generate the frequent patterns. अब हम करेंगे क्या? एक पॉइंटर लगाएंगे और इस पॉइंटर ये टेबल जो यहाँ दिया हुआ है इससे हम पॉइंटर अटैच करेंगे. Now what I will do, इस टेबल को हमने कॉपी किया और F से एक पॉइंटर लिया जो सारे F को कनेक्ट करेगा. No, there is only one F, therefore nothing to connect. I take one pointer from C and connect this C as well as this C because there are two C in the tree. Then I take A, I connect a pointer from here to here. I take M, how many M's are there? 2M, if I connect like this. How many P are there? 2P, if I am going 1P and 1P. Now what I can do, I will. This should have been a little bigger. Just actually, it should be like this. Now, what is the data structure you will use? You will use a data structure which is nothing but if head one, the head should be a pointer type. It should be a pointer type. Therefore, this head will be a pointer. Why do I say it's a pointer? It should be a pointer. बताओ पॉइंटर क्यों कह रहे हैं? Because this will contain the address of that node. F क्या है? Node है ना? उसका एड्रेस शो करेंगे वहां पे. And therefore I will be able to link all those. Therefore I can use a pointer field over there which is going to point over like this. Now this is generation is the session is over. Now what I do is that I have to generate the frequent pattern tree. अब हम करेंगे क्या? Start from the bottom. सबसे पहले कौन है? P. P के लिए कौन कौन सा होगा? Now you should check. P के लिए होगा ये. अरे किए. These two boxes. अब P के ऊपर में कौन कौन सा नोड आ रहा है? P के ऊपर पहले ब्रांच में FCAM, सेकंड ब्रांच में CB. That means if you are going to use this concept, you are getting two branches. एक ब्रांच में FCAM और एक में CB. Therefore इस दोनों P का दो ब्रांच ऐसे हैं जो कि आ रहे हैं. कौन कौन से? Therefore in that case it is going to, I'll just show you this like this. It's called the conditional pattern base. तो conditional pattern base क्या आ रहा है? ये P का बना रहे हैं हम लोग. HCAM और CD, ये रूट था यहाँ पे। तो इसको हमने क्या किया, इस ट्री को हमने सिर्फ 2 ही ब्रांच लिया, एक ये वाला ब्रांच, एक ये वाला ब्रांच, एक ये वाला ब्रांच, और इसके बेस पे हमने ये बना लिया। अब तुम ट्री को हटा दो और ऊपर वाले को पढ़ो, रूट टू M तक, FCAM ये आया। नाउ इसका काउंट 2 आ रहा है, क्यों? Why it is giving you count 2? Because जिस ट्रांजैक्शन में M आएगा उसका मैक्सिमम काउंट 2 ही होगा, बिकॉज M का काउंट 2 है। तो अगर A का काउंट 3 है या F का काउंट 4 भी है तो क्या मतलब है, बिकॉज आई वांट टू फाइंड द ट्रांजैक्शन विच कंटेन्स M आल्सो एंड विच कंटेन्स P आल्सो। तो अगर P का काउंट अगर 2 आ रहा है तो कोई भी ऐसा ट्रांजैक्शन नहीं होगा जिसका काउंट 2 से ज्यादा होगा जिसपे P आएगा। Did you get? Any transaction which is frequent or any item set which is frequent which has P cannot have a count more than the count of P. भाई किस रूल पे बता रहे हैं हम ये? Because support is anti-monotone. The support of the superset cannot be more than the support of the subset. तो P का जब काउंट 2 है तो MP अकाउंट क्या होगा, मैक्सिमम 2 होगा। AMP अकाउंट क्या होगा, मैक्सिमम 2 होगा। CAMP का क्या होगा, 2 होगा। FCAMP का क्या होगा, 2 होगा। Therefore, this value of 2 is because of the count of P. Similarly, take the other branch. इसमें क्या है, P अकाउंट 1 है तो CB 1 होगा, बिकॉज यहां P आ रहा है। अब तुम दूसरा ब्रांच ले लो। अब नाउ लेट अस ट्राई टू गेट द फ्रीक्वेंट पैटर्न। अब यहां पे हमने जब बनाया तो हमने 2 कंडीशनल पैटर्न बेस निकाला P का, FCAM2 और CB1। how much minimum support we have taken? Just see, I have taken minimum support equal to 3. Therefore, you have to only take those transactions which contains 3. अब इसमें F का सपोर्ट क्या है, 2, A का सपोर्ट क्या है, 2, M का सपोर्ट क्या है, 2, B का सपोर्ट क्या है, 1, C का सपोर्ट क्या है, बताओ। C का सपोर्ट क्या है, two plus 1 3, because C will also come in FCAM and C will also come in CB. That means CAMP में CP में भी आएगा C, और C is यहाँ पे C से क्या जनरेट करोगे, CP, यहाँ से क्या करोगे, CP, CP का 2 यहाँ 1 3 हो गया CP का। अब now let us try to find this. You are going to construct a new FP tree based on this pattern by merging all paths and keeping nodes that appear greater than or equal to support times. This leads to only one branch C3. Thus we derive one pattern CP over here. Now why FP has not come? Because FP account जो है 2 आएगा. Why AP has not come? Because AP account 2 आएगा, MP account 2 आएगा, BP का account 2 आएगा. Because when I take the minimum support as 3, I only take those ones which are having a minimum support of at least 3, and therefore it should be at least support greater than or equal to 3, and therefore I generate one pattern over here, CP pattern, one CP from by combining these two. Similarly I do for others. अब किसका लेंगे हम लेंगे M का, M का कौन सा ब्रांच लेंगे, अब देखो कितना इजी हो गया यहाँ पे। M के लिए ब्रांच लेंगे हम ये और ये, and I take these two branches, एक ये वाला ब्रांच और एक ये वाला ब्रांच। पहले M का क्या होगा, कंडीशनल पैटर्न बेस FCA, है ना? इसका क्या होगा? FCA. Now let us try to see. Now just try to see. इसका होगा FCA. काउंट क्या होगा? 2, because M का काउंट 2 है. FCA. दूसरे वाले ब्रांच में देखो, इस ब्रांच में होगा FCA and I will have this M. Therefore, in that it will contain only 1 because यहाँ M1 है, तो ये आएगा. We contain FCA and FCAB. Now you check over here. ये यहाँ पे, ये ऐसे, sorry, ये this one like this, or like this. So it's fine. So like this. Now let us try to check for this FCA2 and FCAB1. इसका होगा ये SC, not this one, इसका ये होगा FCA का 2 और FCA. अब बताओ इसका फ्रीक्वेंट पैटर्न कौन कौन सा होगा? यहाँ पे F का काउंट क्या है? 2 है. F का काउंट 1 है तो F3 होगा. FB जनरेट होगा. C अकाउंट क्या है? 2 है. C अकाउंट 1 है तो इसका C भी जनरेट होगा. A अकाउंट 2 है, A अकाउंट 1 है तो A का अकाउंट 3 है तो ये 3 होगा. तो यानी इसके जो निकलेगा वो निकलेगा, इससे बहुत सारे निकलेंगे. FCAB है frequent. Therefore you will now from this what we generate FCA. We generate FCA. At least having a count equal to 3. Why? Because 2 यहां से और 1 यहां से. अब इसके सब के आगे M है तो कौन कौन इसका फ्रीक्वेंट पैटर्न्स क्या आएंगे? FM, CM और AM, ये वाला. उसके बाद आएगा from here it will give you let me put it from here it will give you this one. Then take 2 combinations FCM, FAM and CM. ये आएगा. पहले सिंगल के साथ M लगाओ, फिर दो के साथ M लगाओ, फिर तीनों के साथ M लगाओ, ये आएगा. तीनों के साथ ये M लगेगा. तो कौन कौन सा फ्रीक्वेंट पैटर्न्स आया? एक तो खुद M आया, FM, CM, AM, FCM, FAM and CM and FCA. That means you get all those frequent patterns. Similarly, you take the another path, ये वाला B का path लो. B यहाँ पे है. Therefore, what you can do is that you have to take one path over here. एक पाथ यहाँ भी है, एक पाथ यहाँ. Take this path, then take this path and take this path. तुम तीनों पाथ के लेके बनाओ, तुम्हारा ऐसे बनेगा. CA का 1, F का 1. Now what after you do for all of them you get like this, and you find here you will get an empty. Why it's giving an empty? Because किसी का काउंट 3 नहीं हो रहा है. F का काउंट 1 यहाँ, 1 यहाँ, F का काउंट 2 है, C का काउंट भी 2 है और A का काउंट तो 1 ही है. देखो empty. यहाँ तुम्हें निकाल के दिखा दिया था ये वाला. A के साथ क्या होगा? ये आएगा FC, and you get all these patterns. And now from here you can generate all the frequent patterns. कौन कौन frequent pattern आया? It is so simple. यहाँ से आया CM, sorry CP. यहाँ से आया FM, AM, CM, FCM, CAM and FAM. यहाँ से आया FA और CA और FCA. यहाँ से आया FC. Then you generate all those from here only. Are you getting it? From P, I get CP, which is frequent. From M, I get FM, CM, AM, FCM, CAM, and FAM, and FCAM. From B, I will not get anything. From A, I get FA, CA, and FCA. From C, I get FC. And these are the frequent patterns that generate from the tree. Okay, I think you have understood this, and therefore, just to make this is the how you are going to generate from there. And now I would like to just tell you why it is fast, because performance shows a big growth in order of magnitude faster than FIRE, and also faster than other tree progression algorithm. Why it is fast? Because there is no candidate generation and no candidate test. It uses the compact data structure because the database is converted into a tree. Thirdly, it eliminates repeated database scans. The basic operation for frequent pattern growth is only counting and tree building. Now these are basically the reasons for it. But there is one big drawback of this tree. The drawback is that once you want to mine a particular tree, the whole tree must be accommodated in the RAM. You cannot use a partition based approach. कि ट्री का एक पार्ट लाया, उससे frequent pattern बना लिया, फिर दूसरा पार्ट लाया, तुम नहीं कर सकते. Because अगर तुम ऐसा करोगे तो क्या होगा कि तुम्हारा जो है वो जो pointers था वो ब्रेक हो जाएगा बीच में. Therefore, it requires a large amount of RAM. Without that, you cannot do. And this is the only drawback of FP3. Fine. And just see the particular time complexity. Now you see this line is for the FIRE. And this is for the FP3. And you see, if I am going to use at the support threshold of 1.5, this will be something around here. Whereas for this, it will go very high. For 1, this value is coming to around 5. For this, it will come to 30. And keep on. Okay. I guess I end this discussion about these things. Anything you want to ask, please. Any questions?
Sir, when will you upload the recordings?
Today itself.
Okay,
I will upload by today or tomorrow by any case. And also I'll upload these PPTs. Though I am telling these PPTs are directly taken from this book of Jan and sorry, not from the book of Tan and Bipin Kumar. Therefore, in that case, you might, even if I do not have this, you can take it from there.